In this video, you are going to learn about what happens when equilibrium is disrupted somehow. Now, the long and short of it is that if equilibrium is disrupted, the direction of the reaction will counteract or balance out this disruption. So the system will shift in a direction to counteract or minimize this disturbance. This is called Le Chatelier's Principle. So Le Chatelier's Principle states that when a reaction at equilibrium is disturbed, the system will shift in the direction to counteract or minimize this disturbance. So we're going to look at different scenarios and determine if these scenarios will cause the reaction to shift to the left or to the right. So let's take a look at what happens if we change the concentration or the quantity of a reactant or product. So let's take a look at our analogy with the sunbathers and the swimmers. Now, the sunbathers are our reactants and the swimmers are our products. And at the beginning of the reaction, we get a lot of people, a lot of sunbathers going into the pool. So the reaction is moving towards the right, towards the products. But we do have a little bit of the reverse happening. So we have some swimmers going back and becoming sunbathers. And eventually we get enough swimmers where we reach equilibrium. And once we reach equilibrium, for every sunbather that turns into a swimmer, we have the reverse happening, a swimmer turning into a sunbather. Now this equilibrium is perfect. It's a one-to-one back and forth equilibrium. But now what happens if we add a whole bunch of reactants? So a big group of people just decided to go into the pool area and become sunbathers. What that's going to cause is a whole bunch of people now are going to be entering the pool. So the reaction will shift toward the product side. And it will take a little while, but equilibrium can then still be reestablished. It's going to look a little different, but we can still have equilibrium established after that disturbance. But it takes a while to get to that equilibrium. So let's take a look at it in the terms of a chemical reaction. So we have N2O4 turning into 2 molecules of NO2. And this is a reaction that has an equilibrium, and let's just say the equilibrium has been established. Now the N2O4, those are the reactants. These are like our sunbathers. And the NO2, these are the products. These are our swimmers. So what we're going to look at is what happens if we increase the quantity or decrease the quantity of each one of these sides. So what this is going to do, if we increase the number of reactants, then it's going to cause a shift to the right. So then more products will start to be produced before equilibrium is established again. So then a new equilibrium has to be established with a new ratio of products to reactants and new amounts of everything. So what happens if we do the reverse of this? What happens if a whole bunch of people decided to jump in the swimming pool? People that weren't even at the pool to begin with. They weren't even sunbathers. They were just random people off the street. A whole bunch of them just jumped into the pool. Well, that's going to probably make you want to leave the pool if you are already in the pool. That's going to cause a shift toward the reactant side. So an increase, if you just take this perfect reaction at equilibrium, you just dump in a whole bunch of product. Now we have, and this is all just new product, you're adding this new product to the system that wasn't there before. It's going to cause a shift to the reactant side of the equilibrium. It's going to cause a shift to the left. So just the reverse of this. Now, what happens if you remove some reactants? So we're at equilibrium, we're starting over, a new equilibrium is established. But what happens if we remove some of the sunbathers? Well, if some of the sunbathers decide to go home, some of the people in the pool might think, well, there's some extra open chairs. Maybe I'll get out of the pool and go sit in those open chairs now that there's no people in them. So if you decrease or if you remove some reactants from this system at equilibrium, the reaction will shift to the left. It'll shift toward the reactant side. And the same thing goes for if you remove some product. So say we're at the swimming pool, equilibrium is established, there's the back and forth happening, but a whole bunch of people that were in the pool decide to go home. Well, what happens if you remove a whole bunch of product from the system? Well, if a whole bunch of people in the pool decide to go home, the people sitting out that are sunbathing might think, well, there's a lot of extra space in the pool. I'm going to go in the pool and swim. So this causes a shift to the product side. If you remove product from a reaction at equilibrium, more product will then be made to compensate for this. That's Le Chatelier's principle. It says that anytime you have equilibrium, so we have this perfect equilibrium, anytime you have equilibrium and you disturb it by adding or removing product or reactant, the reaction will shift in a certain direction to compensate or minimize the disturbance of this equilibrium, and then new equilibrium can be established once enough time has taken place after that shift happens and after that disruption happens. Now let's take a look at another scenario where equilibrium can be disrupted. Now this is a scenario that only takes place if you have gases present. What we're going to do is we're going to change the volume, which would change the pressure. If this was really a gas, it would change the pressure of the container that the reaction takes place in. But let's look at our swimmers and sunbathers analogy and see how this would affect our perfect equilibrium of swimmers and sunbathers in this situation. So we have swimmers turning into sunbathers and sunbathers turning into swimmers. Once that pool starts filling up a little bit, then equilibrium's established and we have that equal numbers of people going back and forth. So this is equilibrium. This is our perfect back and forth equilibrium. But what happens if the pool, and this would never really happen, but what happens if the pool were to just instantly shrink? Well, if you were in a pool and it shrunk and it got smaller, you'd be closer to everyone and you probably wouldn't want to be in the pool anymore. So if a pool were to magically shrink, you would end up getting people leaving the swimming pool because they would be just so close to everyone. Now, if we look at this in terms of a real chemical reaction, what we have to do is we have to identify the number of particles of gas on either side of the reaction. And the reason we need to identify the number of particles is because if we're dealing with gases and volume, the number of particles is crucial. It has a huge effect on the pressure and every other aspect of this reaction. So the number of particles is important. So I'm going to label this. We have 4 gas particles on the left. We have 1 nitrogen molecule and 3 hydrogen molecules. And we have 2 gas particles on the right. We have only 2 ammonia particles. So we start off with 4 gas particles. Granted, they're smaller, but it doesn't matter. It's just the quantity, and we end up with only 2 gas particles. They're larger, but there's only 2 of them. And the size of the actual particle doesn't matter in a gas because they're so far apart, the size of the particle doesn't matter. So what happens if we decrease the volume of the container? This would be like decreasing the volume of the swimming pool. What happens? Now, if we decrease the volume of the container, the reaction will shift in the direction that contains the fewest number of gas particles. So if the volume of the container gets smaller, the reaction sort of realizes that it needs less particles to take up that space, so the reaction moves in the direction that requires the fewest amount of particles to be in there. So the reaction will shift in that direction, the direction that contains the fewest number of gas particles. Now, the opposite happens if we increase the volume. If we increase the volume of the container, the reaction will shift in the direction that contains the most number of gas particles because the reaction realizes that it has room for all of these particles, so now it can go in the direction that contains the most number of gas particles. So when you change the volume, the direction will shift depending on the number of gas particles in the reactant side or the product side. So before you do any work with the reaction shifting, you first need to identify which side has the fewest and the most gas particles on it. Now, what happens if we add an inert gas to this mixture? Now, you know, if we decrease the volume or increase the volume, the pressure changes. But what happens if we add a gas that does not react? That's what we mean by inert. If we add a gas that does not react with the particles that are already in the container. Now we know the pressure will increase because we're increasing the number of particles in the container. But because these gas particles are not participating in the reaction, there's no effect on the equilibrium. This would be like if we had sunbathers and swimmers and a bunch of birds flew over the swimming pool. Now, as long as the birds didn't interact with the sunbathers or the swimmers, it would be just like business as usual. It wouldn't affect the number of sunbathers and swimmers that we had in our equilibrium. So as long as the particles are not reacting, even though now we've added more particles to the mixture, as long as they're not reacting, it will have no effect on our equilibrium. Now the final thing that we can do to disrupt equilibrium is to change the temperature. Now we have this hot sunny day, it's 95 degrees, we have our normal amount of people entering and leaving the swimming pool. Now early on in the reaction we have more people entering the swimming pool until equilibrium is established. And once equilibrium is established, we have the back and forth taking place. Now, what happens if it all of a sudden gets very cold? Our equilibrium has been established, but the temperature changes now, and now it's 75 degrees and cold. What happens to our equilibrium? What happens to our swimming pool, our swimmers, and our sunbathers? Well, if you were swimming and it got really cold, you would not want to be in the pool anymore, so you would leave the pool. This causes a shift to the left. It causes a shift to the reactant side. Now we can still establish equilibrium, but it will look a little different. Our equilibrium will not have as many people in the swimming pool as it did before. So we'll have less people in the pool, but we can still have the equilibrium taking place now at a different temperature. We can apply this to chemical reactions as well, but first let's look at the role that heat plays in this reaction. So if we have sunbathers and we add heat, they will become swimmers. So what you need to do is in every reaction identify what role heat has. Is it required in the reaction or is it released? Now in my scenario of sunbathers and swimmers, heat is a requirement. Heat is a reactant almost. It is an ingredient. It's required. And this makes this an endothermic reaction. So anytime heat is required, you have an endothermic reaction. Now here's another reaction where heat is found on the left. And so when we look at the temperature, the change in temperature and how that affects equilibrium, we have to identify what role heat has in this. So if we put heat on the left side of the arrows, that means we have an endothermic reaction. That means heat is required to get it to go. Just like in our sunbathers and swimmers scenario, if you are a sunbather and it gets hot, you will likely become a swimmer. So heat is a reactant. Now we treat this like heat is a particle. If we were to increase the concentration of heat, what happens? If we were to decrease the concentration of heat, what happens? So go back to the notes you took on concentration, and it's going to be the exact same pattern. So if we increase the heat, we're going to produce more products, because this is an endothermic reaction. If we increase the temperature of our sunbathers and swimmers scenario, we're going to get more swimmers. Now, if it becomes colder, then the swimmers are going to leave the pool and become sunbathers. So they're going to leave the pool and the reaction is going to shift to the left. So that would be what happens in an endothermic reaction. But what happens in an exothermic reaction? So this would be like combustion is a good example of an exothermic reaction. So heat is not required, it's produced in the reaction. So fire, any sort of combustion, fireworks, burning a match, burning a candle, burning propane, all of this is exothermic. So heat is a product of the reaction. This is an exothermic reaction whenever heat is a product. So here, if we treat heat like it's actually part of the reaction, like a particle in the reaction, and we increase the amount of heat of an exothermic reaction, that shifts the reaction to the left, to the reactant side of the reaction. And of course, the reverse happens. If we cool down the reaction, then it shifts to the right, or the product side of the reaction. There's actually, when I dissolve sodium hydroxide in water, it's a very exothermic reaction. It produces a lot of heat. And I can dissolve that sodium hydroxide a lot faster if I cool it down and I put it in an ice bath. That reaction, that dissolving, takes place a lot more efficiently and effectively and quickly if I cool down the container, because it's an exothermic reaction. I can have it shift. I can have more and more product, which is the dissolved sodium hydroxide, be produced, because it will shift that equilibrium to the right. So this is what happens when we change the temperature. The first thing you need to identify is, do I have an endothermic or an exothermic reaction? Now, where does this take place? Of course, we have to realize that this is not just hypothetical stuff that takes place in a lab far, far away. Where do we see this stuff in real life? Where do we see Chateliers Principle in real life? Now, it's everywhere, but one of the easiest ways to describe where we see, or where we can show a real-life example of Chateliers Principle, is in our blood. So we have hemoglobin, and I'm just going to symbolize it using HB. This isn't an official symbol, and this is a super oversimplification, but generally can show what happens. If I have hemoglobin and it reacts with oxygen, binds to oxygen to form a hemoglobin-oxygen complex. Now, in our lungs, we have an abundance of oxygen. And what that will do is that will shift the reaction to the right. So now we'll get more of this complex. And now as this blood disperses through our body and releases into our tissues are oxygen grabbers. So they want the oxygen. They're going to take the oxygen. Then the reaction shifts to the left. So this reaction is just taking place back and forth in a cycle in our body, from our lungs to our tissues, back to our lungs, which are high in oxygen, back to our tissues, which are taking the oxygen, back to our lungs. So this is a perfect example of the constant shifting of the equilibrium reaction that takes place between hemoglobin and oxygen and the hemoglobin-oxygen complex.